Okay, sir, we are preparing the live stream. Okay, sir. So we'll be starting now. I hope the audience is clearly visible to you, sir.
You can hear me well? Or more to the point, can the audience hear me?
So good evening, guys. Physics and Astronomy Club welcomes you to the Cosmic Watch 23. This is our flagship event for this semester. And for the first destination in this voyage, we have Professor Subir Sarkar. He's an undergraduate from IIT Kharagpur, and his main interest lies in the interface between particle physics and astrophysics, cosmological physics, and he's held many prestigious positions pertaining to that and has won many awards. So, to list a few, he led the particle physics, particle theory group at Oxford, and he's also felicitated with Homi Baba Award from KFI, and he's even won the Niels Bohr Professorship at University of Copenhagen. So, without any further ado, I'd like to let him take over the stage, and I think you can start now.
Okay. Shall I start?
Yes, sir.
Okay. Thank you. Well, thank you very much for inviting me. I always thought IIT Kharagpur was the oldest IIT in India, but I just learned that you are in fact a lot older because you had a different name earlier. Well, so it's a pleasure to talk to people who are interested in physics. I'm sure you have realized that during your student years that the one thing that teachers like most above all is when the audience is interested in the subject. And my subject today is something which is perhaps not what most of you are directly engaged with or working on. So I'll try and keep it uh, at an elementary level to start with, and hopefully get on to our recent work, which is something that excites us very much, because it's not often that in one's career one finds something which is literally a very big deal if it turns out to be true. But as always, experiment has to be the judge of that. So what you see on this slide here is a so-called n-body simulation, a computer simulation of the formation of structure in our universe. So this is a so-called Hubble volume, trillion particle simulation carried out on a bunch of computers led by a group at Stanford. And what it shows is that the universe as we imagine it to be today in the standard model of cosmology is not actually either homogeneous or isotropic, because it's full of structure, this so-called cosmic web of galaxies. However, statistically, it is so, because that is the initial conditions from which this structure grew. And what I'm going to ask in this talk is whether this assumption that we make that the universe is fundamentally isotropic and homogeneous is in fact true. And in doing this, I'm going to be guided by something that I learned from my own teacher, in cosmology. That's someone called Dennis Sharma, who I met when I first came to Oxford in 1982 or so. And he is perhaps best known as a famous supervisor. You know, his students were people like Stephen Hawking. He encouraged Roger Penrose to get into cosmology, Martin Rees, many big names. But he was very generous with his ideas himself, and he was surprisingly, for a relativist, a mathematician, he was surprisingly pragmatic. And this quote from his book in 78 says it, that before we ask the big questions in cosmology, the why questions, we should really ask the how questions. And I hope that will resonate with you, because you are, after all, at a Indian Institute of Technology. You are very familiar with the importance of experiment in establishing scientific theories. So my talk will be a little, at times give you a little technical insight into what's going on. But if some of you would like a more kind of descriptive account of what I'm going to talk about, I would refer you to this article I wrote recently for an online journal called Inference, which is actually edited by Sheldon Glashow and a host of other well-known physicists and mathematicians. And this is free to read online, and I encourage you to have a look at it to get a more broader account of what I'm going to say in the next hour. So let's start from the beginning. Just one second. Now, people talk about the standard model of cosmology as if it is something that has only come about in recent times. But in fact, if you look back over history, every culture has had their own cosmology. And some of it going back, 30, 40,000 years, like the Aboriginals of Australia have something called Dreamtime, that is their cosmology. The Mayan civilization, the ancient Hindus, all these people, the Mesopotamians, they had their own cosmology. But in fact, the model that kind of came to be called the standard model, at least in Europe, and which lasted about 2 millennia, was that which goes back to Aristotle and Ptolemy. And in that, we were at the center of the universe, and the sun went around us, and the moon and the known planets, the Mercury, Venus, Mars, Jupiter, Saturn, etc. And then at the very edge, there was this so-called crystalline sphere in which the stars were embedded, because they didn't move on the sky, unlike the planets. And you'll have to agree that this is basically how the universe actually looks. If you look up at the sky, all these things seem to be going around us apart from the stars. Now, this picture was a pretty good, how shall I put it, a pretty good description of what we actually see on the sky. However, we now know in retrospect that it had no dynamical basis. There is no reason for this to be the case. And in fact, this picture was profoundly wrong. And it actually took until the Copernican revolution in the 16th century for this to be displaced and replaced by a new picture in which the sun was at the center, but everything else remained the same, right? We just interchanged the position of the earth and the sun. We were just going around the sun now rather than everything going around us. And there was still this prima mobile at the very edge. So, in fact, for cosmology, that was the Copernican revolution wasn't really that important. However, it had a profound effect 400 years later when Einstein developed general relativity, and pioneers like Alexander Friedman, Georges Lemaitre, and others, De Sitter, Einstein, they developed the first cosmological models. And in doing so, they also obeyed a kind of Copernican principle, in the sense that not only are we not the center of the universe, the sun is also not the center of the universe. In fact, nowhere is the center of the universe. All points are equivalent. So this kind of principle of ultimate democracy, if you like. And that actually is a kind of a practical recognition of the limitations of cosmology, which is different from other physical sciences, because in other sciences you can repeat your experiments, and see if you get the same result. You can do statistics, etc. Whereas in cosmology, we are confined to looking back along our past light cone, and all astronomical information comes on that. We get some data along our past world line, like radioactivity in rocks and stuff like that. And we therefore construct a version of the universe according to what we see. But the point is that we can't move somewhere else and construct another light cone and check that we see the same thing there. So we therefore have to assume, if we want to make any progress, that our position is not special. It is typical. And this was dignified by the name of the cosmological principle. It sounds much more grand. And this term was actually developed by Edward Mill, who was the professor of mathematics at Oxford. And although the notion was already implicit in the work of Friedman and Lemaitre and Einstein de Sitter, who came before him. Now, this was at Oxford, as I said, and of course at Cambridge they had to go one better. So here is Littlewood writing in the 1950s. He says Mill has used a restricted form of the principle, namely that we are not anywhere special in space, but we are still special in time, and you should really abandon that idea as well. And why not go the whole hog and adopt the perfect cosmological principle, which says that we are at a random point in both space and time. And this, as some of you may know, was the so-called steady state theory of the universe, in which it has always existed and is expanding continuously, and matter is being created at a very slow rate to make up for the dilution during the expansion. Interesting harbinger of what came to be later called the inflationary universe. And this was based on the perfect cosmological principle. And this, admittedly, from a philosophical point of view, this is even better, right? It is even more ideal, if you like. However, ultimately, we rely on experiment to tell us what's going on. And as you also know, some years later, in the mid 60s, two radio engineers working at Bell Labs observed with this antenna that you see in the picture that the whole sky was full of thermal radiation at a temperature of around 3 degrees Kelvin. It actually took until 1991 for it to be established that radiation really did have the spectrum of a black body. In fact, it's the best natural black body we know. And the Kobe satellite established that to very high precision. So it wasn't until 1991 that we knew that the steady state theory was ruled out, because you can't make a spectrum as good as that by thermalizing starlight, as the adherents of steady state theory continue to state. However, the spatial part of the cosmological principle still lived on. We abandoned the time part. We recognize that we have a beginning in time, but we still believe that we are at some arbitrary point in space. And the reason, of course, is that we didn't have any data. Remember that when the first cosmological model was constructed, this is 100 years ago, Friedman's paper was 1922. At that time, there was no observations at all. In fact, we didn't even know that we lived in a galaxy. That came a lot later. So, as Weinberg says, if when you have no data, you start with the simplest possible thing. But he did warn that if the data does not fit into the framework, then we shall have to go back to square one, and nothing could be more interesting. And surprisingly, this remark of his in his textbook, from which I learned cosmology, and many of you may have too, this seems to have been rather ignored in the community. So let's go back to the construction of the standard model. So this is based on an assumption of maximally symmetric space-time, which is a way of mathematically formulating this cosmological principle. And then you have general relativity to tell you the dynamics, and then you populate this universe with so-called ideal fluids. So the metric that we use for maximally symmetric space-time is named after Robertson and Walker, although it actually goes back to Friedman and Lemaitre, 20 years before them. And I have written it here in a simple way to make it look like a Minkowski metric, because I'm not using dt, I'm using d eta, and d eta is called the conformal time. It is related to the usual time via the scale factor. Scale factor is the only part in the Friedman, Lemaitre, Robertson, Walker metric, which is dynamic. So it's like a stretching or expansion or contraction of the overall metric, which is assumed to be exactly isotropic and homogeneous everywhere. And what that means is that I can actually map the entire universe using this conformal time onto a little circle, very much like those medieval picture of the universe that I showed you. That picture was from Dante's book. This one is from a modern book. And what it shows is something very similar. We are at the center of the universe because every point is the center of the universe. So imagine you are like sitting on the north pole of a hypersphere, and the Big Bang in this picture is the antipodal point of the hyposphere. So it means that radiation from there can come to us only along the surface of the sphere. So therefore, a singular point, which is the South Pole, can fill our whole sky. And that's why you see radial coordinate is actually conformal time, or if you like, redshift, which is the factor by which the scale factor has been stretched. And all of astronomy is more or less being done within redshift of 1 when the universe was half its present size. And if you go back to a redshift of 1,000, the universe was then hot enough to become a plasma, and you can't look beyond that. And that point, therefore, is the so-called surface of last scattering, where the microwave radiation that we now see as microwave background was released from the primordial plasma. And if you go back still further, the photons would have been random walking in that plasma after having been released from the antipodal point, the singularity on the antipode, which is the surface of infinite redshift. Of course, we don't have a description of physics at that point. This is simply assuming that this metric holds all the way. And this, in fact, illustrates some of the curiosities that arise when we do that. So we can see that if I consider 2 points on this last scattering surface, whose past light cones are just barely touching, their angular separation is about 1 degree, which means that if I pick 2 points which are further apart than 1 degree on the microwave background sky, they have never been in causal contact. And yet their temperatures are the same to within 1 part in 10 to the 5, right? Something clearly very mysterious there. So obviously this picture cannot hold all the way back to the initial singularity. Something must happen at some early time to put into causal contacts these points, which are apparently cannot be so in this space-time diagram, right? So that's inflation. That's a topic for another day. Let me carry on with what we do with this metric. From the metric G mu nu, you can construct the curvature tensor. You can construct the Ricci tensor, the scalar curvature. Perhaps all of you have not had courses in general relativity. So all that is necessary for you to know now is that Einstein told us how to take a metric, which is like graph paper. It tells you how to measure distances between events in space-time, and how that metric and quantities that you construct from the metric, which have indices that run from 1 to 4, they are tensors, how these relate via the Newton's constant of gravity to the energy momentum tensor, which is on the right hand side. So as Wheeler famously said, space-time tells matter how to move and matter tells space-time how to curve. And this very elegant equation, which hides a great deal of complexity, is our current best description of gravity. Right? I say very complicated because you see there are 16 equations, but actually G mu nu is symmetric, so there are only 10. But even 10 coupled equations is a lot, and we can't in general solve them. It's only when you have some extreme symmetry like this metric here that we can even hope to solve Einstein's equations. So this is why we can simplify this equation to the so-called Friedman-Lemaitre equation, which is just a simple differential equation that an undergraduate can solve. Even a high school student can solve it, where it tells you that the rate of change of the scale factor, excuse me, A dot, is related to the energy density in matter, rho of m, the curvature of spatial sections, this k over a square, and a something called lambda over 3, which is called a cosmological constant. And basically, if I rewrite this equation in terms of the present rate of expansion, h sub 0, which is around 70 kilometers per second per megaparsec, then I can write it in terms of the fractional contributions of the matter density, the curvature, and the cosmological constant, which are defined so. Omega matter is rho m over 3h squared by 8 pi g. This is the critical density, and so on, right? And of course, I've told you already that the redshift is simply the ratio of the scale factor at the time when the radiation was emitted to when it is observed. And we normalize it by subtracting 1. So the redshift is 0 today. Now, this equation therefore encapsulates all that there is about the standard model. But at this point, I should point out that this is very important because everything that is being done today in cosmology is based on dividing this equation through by h naught square, in which case you get this so-called sum rule that the fractional contributions of matter, curvature, and lambda add up to 1. You'll see how important this is. But first, let me point out that when this equation was first written down, this was in the 1920s, then at that time, we only knew about non-relativistic matter, dust. But in the 1930s, quantum field theory started being developed. And people like Pauli and Zeldovich and so on realized that this T mu nu should include the energy density of quantum fields. And that includes the 0-point fluctuations. And those 0-point fluctuations actually contribute a energy density, which acts like a cosmological constant in the sense that there is a term on the left-hand side of this equation which multiplies the metric. And this is allowed to be there because of the underlying symmetry, because there is general coordinate invariance or local coordinate invariance, and reflecting that, you can always add a term like this and the dynamics will be unchanged. So it's not a matter of whether Einstein adds it or somebody else adds it. It's not their choice. It has to be there because it's allowed by the symmetry of the equation. And that little lambda, which is something that looks like part of the geometry on the left hand side, will add to the contribution from the quantum fields to the energy momentum tensor on the right hand side. So the net lambda, this capital lambda, is the sum of these two completely unrelated terms. I emphasize that these two terms know nothing about each other, and yet it is the sum that enters into this cosmological equation. And omega lambda, which is lambda over 3 times h naught square, this is the quantity that will then determine the evolution of the universe. And it has to be there for something of order h naught square in order to be of order 1. So you can see that this model itself is imprinting a scale on what lambda can be if I interpret data in the framework of this model. But let me carry on. If I have lambda as an important component, it turns out that because of Lorentz invariance, the vacuum should look the same to all inertial observers. So lambda has to have an equation of state such that the pressure is the negative of the energy density, right? And if you have P equals minus rho, then if you look at the second Friedman equation, which is really a vast simplification of the Raychaudhuri equation, then because you have rho plus 3p as governing the rate of change of the Hubble rate, the acceleration, then if this is negative of rho, then the whole thing can be negative, and what looked like deceleration can become acceleration. You might ask, why is 3p entering here? That's because in general relativity, all energy density gravitates, and that includes kinetic energy, and pressure, as you know, is just kinetic energy of whatever is moving about, contributing the pressure. So in late 90s, uh, when people started studying type 1a supernovae, which as you see in the top right panel, are basically giant thermonuclear explosions of stars, and the light curve, which basically the star becomes as bright as the whole galaxy and then fades away over a period of weeks. This is called the light curve. And the width of this light curve and the height of the light curve, as you'll see later, are correlated in a way that allows them to be used as standardizable candles. In other words, we know how much energy they're putting out. So if you measure their magnitude and compare it with their redshift, then as is shown in this popular article by Saul Perlmutter, you actually can tell the difference between an expansion which is accelerating or going at constant rate, that's the empty universe, or decelerating, right? And the indication was that the universe is accelerating. In fact, he's now showing this in terms of the time. This is actually not what you directly measure. The time is inferred from the redshift in the framework of a model, because all observations are being done at one point in time today, right? In my last slide of the talk, I'll tell you something about how to go beyond that. But you see here, the observations are suggesting that the universe has not always decelerated, that it first decelerated and then it accelerated if you go back about 4, 5, 6 billion years into the past. But the acceleration began quite recently, okay, at a redshift of around 1. And as you all know, this discovery of the accelerating universe was awarded the Nobel Prize in 2011, and that made a huge impact on the field. People kind of ignored the issues that I had raised in the last slide, and everyone assumes that this is true. The universe is dominated by vacuum energy. The point is that they inferred this by combining observations. So, for example, those supernova observations that I showed you give you a combination of omega lambda minus omega matter. So, if I plot it on this figure here, that is this diagonal banana that you see here, okay, with the uncertainties. These are two different groups, Supernova Cosmology Project and High Z Supernova Search Team, that made the observations. They were consistent. Now, you also have a constraint from the cosmic microwave background. Those fluctuations that we saw in the sky, they have a characteristic scale of 1 degree. So if I take the power spectrum has a peak at a multipole of around 200, which corresponds to about 1 degree. And as I showed you in the previous figure, that angular scale is a measure of the causal horizon on the last scattering surface, and it turns out to be proportional to the square root of omega curvature. So that is a measurement of omega curvature, and omega curvature is 1 minus omega lambda minus omega matter. So you get this diagonal constraint here. And then you have observations of things called baryon acoustic oscillations. These are just like the fluctuations in the microwave background, except that these are in the baryons, which were coupled to the radiation, but they're much, much more faint because the baryons are today subdominant part of the universe. They are overweighed by a factor of at least 5 to 6 by the dark matter, which doesn't couple to photons. So that gives you a measure of the matter density. And if you put all this together, you can see that they pick out a point where omega lambda is 0.7. And if you remember the definition of omega lambda, lambda over 3 h naught square, that means lambda is about 2 h naught square. And this is the real scale of lambda, the present day Hubble parameter, okay, which in particle physics units is about 10 to the minus 42 GeV, or if you like, the inverse of 10 to the 28 centimeters, which is the size of the Hubble radius. So it's very much an infrared scale. It is not a constant, it is not fundamental. And yet, the very structure of the model in which we are inferring this conclusion about lambda from the data is forcing that scale upon it. Now, I don't understand really why people didn't tweak to this, that therefore it must be a feature of the model. It may not be genuinely the case that there is a lambda of order h naught square in nature. Now, a lot of people think that the microwave background observations, which are very precise, by this one is from Planck, has established this standard model beyond all doubt. That's in fact not true, because this peak, as I said, is proportional to the curvature, not to lambda. Lambda has no direct influence because at the time of last scattering, the redshift was 1,000, which means the matter density was 1,000 cube times bigger at the time. And lambda was not different from today. So it was subdominant by a factor of 10 to the 9. It had no influence at all on the damped oscillations in the photon baryon plasma, which have left these imprints. So we really must ask whether this observation is in fact valid. But people don't actually tell you that lambda has a scale of 10 to the minus 42 GeV, which would make it pretty evident that this is something which is imposed by the cosmological model. They actually write it in Planck units, which means that they divide by 8 pi g, which is the same as multiplying by the Planck mass, which is Planck mass is 10 to the 19 GeV. So you see that the energy scale that you infer for the so-called dark energy for the cosmological constant is the geometric mean of the Hubble radius 10 to the minus 42 GeV and the Planck scale, which is 10 to the 19 GeV, and you end up with 10 to the minus 12 GeV or a milli electron volt, which is of course the temperature of the microwave background. And this is not a coincidence. This is by construction. But people write papers about what a fantastic coincidence this is. Now, what does particle physics tell us? I mean, we are very proud of our standard model and it explains everything that we measure in the laboratory, etc. We can write down a Lagrangian for it. And it is definitely, I would say the greatest intellectual achievement of humankind in the past century. We can write down a Lagrangian. I've written it here in kind of compact notation in terms of gauge fields. These are this F square. So you have the, F square could, for example, be E square plus B square. That's the gauge invariant combination for the electromagnetic field. You have something similar for the weak interactions where you have W and Z bosons. You have something like that for the gluons, the strong interaction, where the gauge field part is more complicated because they are non-abelian gauge fields. They interact with themselves, unlike photons. But the structure is basically this, and the psi's are fermions, and the phi is the Higgs boson, for which we have this standard Mexican hat-like potential, although we have now measured the mass, and we now need to measure the shape of that potential, which is the task of the Large Hadron Collider over the next 20 years or so. And from that, we hope to learn what lies beyond. Of course, we can always write down an infinite number of operators to add to the standard model, which are of dimension more than 4. So they are not renormalizable, and they would correspond to terms which break the symmetries of the standard model. So, for example, I could write down a dimension 5 term which violates lepton number and can give neutrinos a Majorana mass. Or I could write down a term that violates baryon number and makes protons decay. Now, they are damped by powers of this cutoff, m. M is the scale up to which the standard model is presumed to be valid, and m can be some high value if you don't see any new physics up to that scale. So you can immediately see that it is quite natural to understand why neutrino masses should be small if m is very large, why we have not seen proton decay yet if m is large. But this kind of argument is a bit challenged by the fact that there are two terms that I can write down which are actually of dimension less than 4. And one of them, this m square phi square, that is the notorious correction to the Higgs mass. If the Higgs is a fundamental particle, then as it propagates to the vacuum, it couples to everything it sees in the vacuum, every particle. And in particular, for example, it will couple to the top quark because it couples proportional to mass. So the top quark Ikawa coupling appears here. And when you do the integral of the radiative correction of the top quark loop, that does not go as log of m, it goes as m square. It is a quadratic divergence. Why is that? That's because the Higgs is not a fermion, it's a scalar. So for an electron, this problem does not arise because if you try to calculate the radiative correction to electron mass, uh, because it is got spin half, if you take the mass to 0, you get by conservation of helicity, you will have a distinction between particles that are spinning left and spinning right. And that controls, or rather protects, the mass and prevents it from diverging as anything more strongly than log of the cutoff, which is under control. But when you look at a scalar particle, a fundamental scalar like the Higgs, then the problem is that it diverges quadratically. And the efforts of particle physicists over the last 30, 40 years has been to try to understand how to control that divergence. So they have invented notions called supersymmetry, in which you have some new, particles which are the supersymmetric partners of the known fermions on bosons, because this correction is of opposite sign for them, so it can cancel out. Or you could say that the Higgs is not a fundamental particle, it's composite. So after all, we do know scalars like, say, the pion. It's a scalar particle, but we don't worry about the mass divergence of the pion because it's made out of up and down quarks. It's composite. And so therefore it has a form factor. It will not have this quadratic divergence. And these ideas have so far not been found to be realized in nature, but the search continues. But my point today is to focus on this other term, which is the second renormalizable term of the, super renormalizable term of the standard model, which is the 0 point energy. And its natural scale would be this m to the power 4. So you can see that given that we have tested the standard model up to TeV energies at the Large Hadron Collider already, the smallest value it can naturally have would be of order a TeV to the fourth power. And that's a factor of 10 to the 60 times larger than what cosmologists tell us it is, right? And that is something that you cannot ignore. Okay, if I let this 1 TeV go to 10 to the 19 GeV, then this becomes 10 to the 120. But of course, we don't know that the field theoretical description of nature is valid to the Planck scale. So, I find a factor of 10 to the 60 bad enough. I don't need to make it 10 to the 120. More to the point, what this means is that our entire picture of the evolution of the universe, which is the idea that it's sort of cooling down from the Big Bang, and then it undergoes all series of transitions and symmetry breakings and so on to give us the universe today, that becomes problematic because the electroweak scale would have been reached about 10 to the minus 12 seconds after the Big Bang. So at that point, this vacuum energy should have come to dominate, and the universe should have gone into exponential expansion, de Sitter phase, forever. There is no way it can end, that the universe can exit. So there must be some reason why it didn't happen, and a possible explanation was given by Pauli. He was writing in the Handbuch der Physik in 1933. It is obvious from experience that this 0 point energy does not produce a gravitational field. Now, Pauli was actually writing the article on general relativity. And he, of course, knew very well that in GR, all energy density couples to the gravitational field. So there is no reason why this vacuum energy should not. Unfortunately, Pauli didn't tell us why he thinks this should be the case. He was just making an empirical observation that 0 point energy cannot couple to the gravitational field. Otherwise, you would not be here talking about it. So what has happened is in the intervening 90 years, every theoretical physicist in the world has thought about this problem, the cosmological constant problem, and has unfortunately failed to solve it. It is Steven Weinberg called it the bone in our throat. It is the biggest problem in theoretical physics. I think one can say, arguably, that is the case. And we don't know why this is the case. And yet we ignore it and then talk about vacuum energy in the sky driving the expansion of the universe. In fact, recent work by Giadwali, which actually comes out of a realization that started first in the mid 80s when string theory started becoming popular, is if you have de Sitter space, which is dominated by a cosmological constant, exponentially expanding space, that has no future infinity. And then you can't even do the simplest process that a particle physicist wants to do, which is scatter two particles and have them come in, scatter, and go off to infinity. So in other words, you can't formulate an S matrix. And S matrix we consider to be a fundamental thing. Without that, we can't do physics. And it turns out that therefore we can't have, possibly we can't have reconciliation of these two things. And therefore, maybe nature prohibits de Sitter space for some deep reason. So these are interesting ideas which some of you might like to think about. Let me just say for the more technically minded amongst you, that scale of millielectron volts in terms of distance corresponds to about a tenth of a millimeter. So you might expect that something funny might happen to gravity at that dark energy scale. For example, the inverse square law might get a additional component. Let's parameterize it in terms of some kind of equal-like coupling and try to measure this alpha, this coefficient. So as you see here, people have built very, very sensitive Cavendish balance style experiments, and they have actually probed down to very, very small scales of the order of a fraction of a millimeter, and they have put upper bounds on this alpha, which are already a factor of 10 and more below where it should naturally be. Of course, there is plenty of room at the bottom. You could go further down still. They will be limited by technology, and but the point is that this was a natural expectation and it has not been fulfilled. And then people propose even more baroque things like screening mechanisms. Maybe dark energy has effect only when there is no matter in empty space and not near the earth. So in principle, you can't ever detect it by any experiment. So I personally am not too enamored of theories which are constructed so as to evade experiment. So let's look at what observations of the universe actually are telling us. So this lambda CDM model plus inflation actually has a great success. It does reproduce the observed so-called cosmic web of galaxies. And really, this is what our universe looks like on the larger scales. This is a map made by the Sloan Digital Sky Survey. But if you look on smaller scales, we are at the center of this picture. If you look at the innermost 200 megaparsecs, this has been mapped by Brent Tully and collaborators. This is the Cosmic Flows 3 survey. And we are part of the Virgo cluster. We are actually moving, as these thin lines indicate, towards the Shapley supercluster. The scale of this is about 200 megaparsecs. So a megaparsec is, of course, a million parsecs, and a parsec is 3.3 light years. So our nearest galaxy for normalization is Andromeda. That's about zero point 0.8 of a megaparsec. The question you should ask is, if you look at this picture, is does it really look like a homogeneous distribution? I mean, the universe may well be statistically homogeneous and isotropic on large scales, but when we make measurements locally, when we try to measure the Hubble parameter locally, some of you would have heard of the Hubble tension, which is a discrepancy between the value of the Hubble parameter measured locally and that inferred from the cosmic microwave background. My question would be, how can you measure the Hubble parameter in such a complex density field as that, where in fact the expansion rate is varying over the sky by as much as 10%? Can we assume that we are a typical observer? Should it not matter if you are in an overdensity or in a void? Should it not matter what direction we look at? Are we looking in this empty direction or are we looking along matter? Our past light cone will respond to the distribution of matter along it. So these are all questions that we can now ask today because we have data today, right? But let me go back to an observation that was made a long time ago, back in the 60s, which is that the cosmic microwave background is not actually isotropic. This is something you're told in your lectures, that the universe is isotropic, but the CMB is not. It has a huge dipole anisotropy. As you see, half the sky is hot and half the sky is cold, and the temperature varies with direction from this hotspot, this cos theta, uh, according to this formula. So we interpret this as due to our motion at a velocity beta along that direction. This formula is a special relativistic formula. It was derived by Peebles and Wilkinson in 68, and it fits the data pretty well. And the velocity that we infer, because this temperature variation is about 1 milli and the overall temperature is it's Kelvin, so it's about 1 part in 1,000. So beta is also about 1 part in 1,000. It's in fact 370 kilometers per second. So we think that this is because we are moving with respect to the frame, and the microwave background is really isotropic. And if you boost to that frame, then the universe is isotropic and the Friedmann-Lemaitre equations should be valid there. Why are we moving? Well, because we know there is local inhomogeneity, so something is pulling us. But then that something which is pulling us should be relatively close by, because on large scales, the universe is meant to be homogeneous. So we should converge to the microwave background frame on scales larger than 100 to 200 megaparsecs. So we transform all data to the frame and anticipation of that being true, and then apply the equations and infer what we infer about the universe. And then people say this must be true because if we count galaxies in spheres of increasing size, then in fact they say that beyond 100 megaparsecs, the number counts do start scaling as r cube, in spite of all the inhomogeneity you saw. So all this holds together. Now, this dipole anisotropy in the microwave background was actually predicted by Sharma and Stewart. As he sees here, if the microwave radiation is cosmological isotropic, it will only be so to an observer who is at rest in the frame of distant matter which last scattered the radiation. So what Sharma and Stewart knew was that we are not in that frame because we have peculiar velocities. We are not all going away from each other in the Hubble flow on small scales. So Andromeda, for example, is not going away from us, it's falling towards us, right? That's a peculiar velocity. And he therefore predicted that there should be a dipole, and this was soon found, amongst others, by George Smoot, who later got a Nobel Prize. And what he's showing in his Nobel lecture is that this motion of ours is kind of complicated. As I said, Andromeda and we are falling towards each other. And we are, in fact, orbiting around our galaxy in roughly the opposite direction to the direction of the hotspot in the microwave background. So the two velocities add up, and our net motion is about 620 kilometers per second. It's about double that. And this is actually shared by the local group, which is Andromeda, Magellanic Clouds, and so forth. So we are moving because something which we call the great attractor is pulling us. And this great attractor should be pretty close by in order that it be responsible for our motion. You see, the further you put the great attractor, the more massive it has to be by the inverse square law. And, we can't afford to put it more than about a couple of 100 megaparsecs away. However, we haven't actually seen convergence to the CMB frame, but we still continue to correct data by transforming to it. And here is the observations of the local so-called bulk flow as a function of the averaging volume, here given in terms of megaparsec over little h. Little h is the Hubble parameter in 100 kilometers per second per megaparsec. So it's about 0.7. And inverse of that is about 3/2. So you see that this purple line is the expectation from the standard lambda CDM model as to how this velocity should fall off as I keep averaging over bigger and bigger boxes. But the data, such as it is, does not follow that trend. Now, you will observe immediately that the data has large error bars because these measurements of the bulk flow require that we rely on distance measurements which have nothing to do with the redshift. You can't use the redshift because this is not the Hubble flow. So you have to have an independent way of knowing the distance to distant galaxies. And for that, we use things called the Tully-Fisher relation, which is some empirical correlation between the the velocity with which the stars are orbiting in spiral galaxies and the luminosity of the galaxy. Or there is something called the fundamental plane, which is a similar relation for elliptical galaxies to do with the velocity dispersion and the size of the object. Now, these observations are therefore very uncertain for that reason. But just 2 weeks ago or 3 weeks ago, Brent Tully's group came out with two new data points, which I have indicated here in red. And as you see, the indications are of a clear discrepancy from the expectation. Now, of course, in principle, the fluctuations in the microwave background, the growth of structure, all these are happening from some initial fluctuations, which are meant to be some kind of a Gaussian random field. And in a Gaussian field, anything can happen with small enough probability. So you could say, well, this is some fluke. We happen to be in a region of the universe where there is a large, deep bulk flow, but it is just a statistical anomaly. So you could ask, how anomalous is that? And the answer that we had given earlier is 1% based on this measurement we had made, C11, that was Colin et al. 2011. But the new measurements are now telling us that that unlikelihood is now at the level of 0.002%. You can look up this new paper to check that. So we are definitely not Copernican observers. If you recall, that's how we started constructing cosmology. And this has implications for how we analyze data, what sort of covariances we employ, etc. But let me come to something much simpler, non-technical, which I hope all of you can engage with, which is that if the dipole in the CMB is due to our motion with respect to this ideal frame where the universe looks isotropic, then we should certainly see a same dipole in the distribution of distant sources. And this is an effect called aberration at a different angle than the one where it actually is. And this was first discovered by James Bradley, who was also a professor here, a civilian professor of astronomy. And 200 years before Einstein, he actually discovered something which you can see is a special relativistic formula, that the angle of the star is related to our motion, v over c, which then gives you what the exact angle that it will appear compared to its true angle, right? And this is because of the finite speed of light in reaching us. In fact, Bradley worked out the speed of light from this to within 10%, right? Impressive. Now, of course, if you're looking at an object which has got some kind of a spectrum, then we also have to be careful as to what part of that spectrum we sample when we are in a moving frame of reference, because there will be a Doppler shift. So, for example, if you're looking at objects which have some distribution in flux as a function of frequency, then if we have some flux threshold, we only see objects above some particular flux, then the number of objects which we'll see above that flux level will be boosted in the direction you're moving and will be diminished behind us, right? So Ellis and Baldwin, George Ellis is a relativist from South Africa, and John Baldwin was the head of the radio astronomy lab at the Cavendish Laboratory in Cambridge. They worked out in back in 84 that you should therefore see a dipole in the motion in the distribution of distant sources, which is very much like the one in the CMB, v over c cos theta. But now you have some additional term which has to do with the exponents of this power laws of the power law spectrum and the power law distribution of the fluxes, which is usually the case. So they said you need to do this test in order to check that the kinematic interpretation of the microwave background dipole is correct, right? So just to show you pictorially, if I'd have an idealized isotropic distribution of sources, then if I'm moving in that direction towards the red dot, then I'll see a little clustering of objects around that point and a diminution in the opposite direction. So this is the dipole. Okay. Of course, I've exaggerated the effect here so you can see it. The actual effect we're going to be looking at is of order 1%. And we have therefore to get a lot of objects to see such a tiny effect. And we have been able to gather a catalog of 1.5 million quasars. This is due to my collaborator Nathan Secrist, who is at the Naval Observatory in Washington. And our other co-workers are Mohammad Ramiz, who is a reader at the Tata Institute of Fundamental Research in Bombay. Sebastian von Hauseger, postdoc working with me here at Oxford. And Roya Mohai and Jacques Collin are at the Institute of Astrophysics in Paris. So we found this catalog of quasars that Nathan had created based on observations made by this infrared satellite, WISE, in various bands. And our stroke of luck was that some of these quasars had their redshifts measured very precisely by the Sloan Digital Sky Survey, right? And the distribution, the histogram of the redshift shows that they are all at cosmological distances. About 99% of them are more than redshift zero point 0.1. Redshift of 0.1 means a distance more than 300 over little h megaparsecs. So in other words, they should be subject to this aberration effect. So when we smooth this map and we see this dipole, and then we have to estimate the dipole with an estimator that has no bias, etc. And then we can look at the spectral index and the flux distribution of all these 1.5 million quasars, which are shown here. So what we do is that we then create mock skies. We do a Monte Carlo simulation where we draw from these two distributions at random and create mock skies and ask what the dipole in the mock sky looks like compared to what we actually see, to test whether the null hypothesis, namely the standard model, is correct, right? So what we find is that our motion is indeed, according to the dipole in the quasars, in roughly the same direction as the microwave background, okay, within the error box. But the amplitude is much higher, okay. You can see it's over a factor of 2 larger than what you expect, according to the 10 million simulations that we did. And in those 10 million simulations of what we expect in the standard model, the dipole is this Gaussian distribution that you see here, but and only 5 of this 10 million by accident get up to the amplitude that we actually observe. So, very transparently, the p-value is 5 times 10 to the minus 7. And if I try to translate that into sigmas, for a one-sided Gaussian, that is 4.9 sigma. So in other words, this is a significant signal, and it confirms a previous indication that Ashok Singhal, who is a radio astronomer in India, had got earlier with a radio catalog which had less sources, and the significance of that was only 2.8 sigma. But 4.9 means it is time to take it seriously. In fact, what you have done is you have combined the radio source catalog and cleaned it up further with the WISE catalog, which is much, much bigger. And when we combine these two, we find that actually the two dipoles are consistent with each other. In other words, this is done at radio frequencies, this is done at infrared wavelengths, so the very different. And it's the same dipole, so there is no frequency dependence, which some people had claimed. And we know what the vector mean is. And if I combine the significance from these two, now we are exceeding 5 sigma, which is the gold standard, at least in particle physics, for when you really take something seriously. Now, what is the community saying about this? So here is the doyen of the community, Jim Peebles, who is really the father of the standard model. And he wrote a review on current anomalies in cosmology. And he says the anomaly that we are talking about is as well established as the Hubble tension, yet the literature is much smaller than the hundreds of papers with the phrase Hubble tension in the abstract. And then he says, I expect the difference is an inevitable consequence of the way we behave. I don't know what he means by that, but I leave it to you to figure it out. Just to say that we have made our catalog, the data, everything public because we believe in open science. And another group from Australia has done a Bayesian analysis on it, and they claim an even higher significance of this anomaly, 5.7 sigma. They also do something interesting. Uh, Dalang and Bonva had suggested that maybe you can get a high dipole because of a correlation between the spectral index and the flux index, this X and alpha parameters that I mentioned, evolving in some, conspiratorial manner. But these guys showed in a data-driven way that that can't account for the effect. Okay, if I could have another 10 minutes, I'll just tell you what the implications of this are for the standard deductions from cosmology, in particular for cosmology with type 1a supernovae, which, as I told you, are thermonuclear explosions which have no hydrogen in the spectrum, but they do show the spectral line of silicon. And basically, the taxonomy of supernovae is based on looking at this kind of indicators to decide if they are resulting from the collapse of the silicon ion core or a gigantic thermonuclear explosion like a hydrogen bomb. We don't really know what does this. It could be binaries coalescing. It could be a compact object accreting from a bigger star. But all we know is that they go bang and they have these light curves, which have now been measured in exquisite detail using CCD cameras, which monitor the sky continuously. What the advantage of that is that if a supernova goes off, and then you notice it here at the peak, you can actually go back a week or two to see what the flux was on the rise time. And that's very important because then you can measure the width of the light curve. And that we'll see is very crucial for supernova cosmology. And people measure it in different bands. This is a definition of the bands and the wavelengths. So essentially, you measure the peak magnitude and the redshift of the supernova itself or the host galaxy. They don't differ by very much. Now, the light curves, as you see here, show a lot of scatter. They're not standard candles. But a man called Phillips at Anglo-Australian Telescope determined that there is an interesting anti-correlation between the peak magnitude and essentially the width of the light curve. And that slightly changes according to what band you're looking at. So it's a color dependent effect. And if you see, if you stretch the light curves according to this observed anticorrelation, then they all fall on top of each other. Okay, so essentially you can adjust the magnitudes according to the width of the light curve, and then the scatter is reduced to a factor of 2. So you can start doing cosmology. I mean, you don't understand why that happens theoretically, but it's empirically valid. Now, cosmology says that if you have measured the magnitude, from that you work out the so-called luminosity distance by this formula. And the luminosity distance is given in the standard model in terms of usual parameters, omega matter, omega k, omega lambda. Now, this is how you worked out that difference of omega lambda and omega matter, the diagonal line in that plane, which was construed as evidence for acceleration. Now, to be precise, you don't really need a cosmological model because most of the supernovae we are looking at only go out to a redshift of 1 or so. So we can actually do a Taylor expansion of this luminosity distance in terms of the velocity, the acceleration, the rate of change of the acceleration, and so on. So this quantity Q naught, this is the way astronomers had defined the acceleration, because this was done at a time when you expected the thing to be, the universe to be decelerating. So they defined it in such a way with a minus sign that it would come out to be a positive number. Surprisingly, it turned out to be a negative number. And we can do this cosmographic expansion. But first, I want to make a point about the way that statistics is done in supernova cosmology. I believe it is unprincipled because what they do is they construct a chi-square where you take the observed magnitude and you subtract from it the theoretical, the expected value in your model, square it and divide it by the uncertainty of your measurement square. This part is perfectly kosher. But what they then do is that they add a second uncertainty in the denominator here and they adjust it until they get chi-square per degree of freedom to be 1. Now, that is not principled because what that just means is that if the data is not fitting your theory, you just keep enlarging the error bars until they do, right? So if you do that, you are not, you're fitting to a model, you're not doing model selection. So we actually use a maximum likelihood estimator, which basically says that what I'm measuring is the likelihood is that of seeing the observed data given a model, and I can factorize that into something that depends on supernovae and that something that depends on cosmology. And my master student Jeppe Nielsen, when I was in Copenhagen, noticed that the actual corrections that the observers make for the stretch correction and the color corrections which they publish, they are actually roughly Gaussian shaped, so that we can approximate these functions to be Gaussians. And then we can integrate the whole thing analytically and we can construct a likelihood in 3 lines and we can determine the uncertainties and everything in a rigorous way. So when we now do a cosmographic analysis of the supernova data from the joint light curve analysis catalog, which was 740 supernovae, we find that if I let the maximum likelihood estimator loose on it and allow this Q naught to have a monopole term and a dipole term, right? I'm trying to keep the number of parameters small, so I'm just allowing one extra parameter. The MLE then says that the acceleration that is inferred from the supernovae is just in one direction, this hotspot that you see here, right? Which is in fact within errors consistent with the direction of the CMB dipole. And the magnitude of this dipole acceleration is actually 50 times bigger than the monopole component, if any. And the monopole, as you can see here, is actually consistent with 0 at just over 1.4 sigma. Whereas the dipole anisotropy, which should not be there at all if it is due to lambda, lambda should make the universe accelerate isotropically. So the standard lambda CDM model is up here, this star here, and you see that is excluded at nearly 4 sigma. So therefore, what we conclude from this exercise is that the cosmic acceleration that is inferred from supernovae may be just an artifact of our being located in a deep bulk flow which is moving in that direction, which in fact includes most of the observed supernovae and is not due to lambda at all. So this mismatch of the matter frame and the microwave background frame that we have found at over 5 sigma really means that you have to go back to uh, ground zero in cosmology. You have to start with a new cosmological model. Now, unfortunately, as I told you, exact solutions of Einstein's equations are extremely hard to come by, and they become very complicated, and we have still got only a finite amount of data. So nobody really wants to go there. But we may be left with no choice in the matter. But of course, first we need much more data in order to try to quantify how this mismatch arises, at what redshift does it arise. We need to do tomography of this dipole with redshift. And for that, there is data coming from lots of new surveys. There is the LSST on the Rubin telescope, which is now being constructed in Chile. We have joined that project and we'll be getting data from it hopefully next year. Next year also the Euclid satellite will fly. That will also map about a third of the sky. And then in the longer run, there is also the dark energy survey instrument on the Mayal telescope at Kitt Peak in Arizona that has already got several million spectroscopic redshifts. So a lot of data is coming. And so theories have been encouraged, meanwhile, to start constructing models which have anisotropy, which are not isotropic metrics. But the fact is that we are, at the moment, the standard model of cosmology, which, as I said, is based on the assumption of homogeneity and isotropy, uh, has never actually been rigorously tested. We already have enough data to test it and not just measure its parameters with precision. That is become the buzzword in cosmology today. And this finding, therefore, that the rest frame of distant quasars and radio sources does not coincide with the CMB rest frame, in other words, the frame in which they look isotropic, this is a fundamental challenge to the assumption of this Friedman-Lemaitre-Robertson-Walker metric, right? Of course, it could be a systematic error of some kind. We have looked very hard for the last couple of years. As I said, we have made our data public. Nobody has found anything wrong with anything we have done. They have also found the same result. But given what is at stake, it is still worth considering that question, and most importantly, getting new data sets with which we can check this. But meanwhile, I would argue that the standard procedure, which is that we boost all the things that we measure, redshifts and magnitudes, to this hypothetical cosmic rest frame, and then we also make corrections for the peculiar velocities of the host galaxies and so on, and then infer cosmic acceleration and then interpret it as due to lambda, and then we call it vacuum energy. This whole business is totally unjustified. The point is that when we actually analyze the data in the heliocentric rest frame, then we see a clear dipole asymmetry in both the recession velocities and the inferred acceleration. And therefore, cosmic acceleration might just be an artifact of our local bulk flow. And one way that we'll know this in the future is with this telescope that is also being constructed in Chile, the extremely large telescope. And what it will have is a new instrument, which is amazing marvel of technology. It is called a laser comb. And a laser comb can measure shifts in wavelength of 1 part in 10 to the 8. So when you say that the light from a distant galaxy is redshifted, that redshift is, of course, something that changes every day because that object is moving further away from us, right? So let's make an estimate. So the universe is 10 billion years old. So every year, any parameter will change by of order 10 to the minus 10 per year, right? With some coefficient which you have to calculate. So in 10 years, it will change by 10 to the minus 9 per year. And if we consider 100 Lyman alpha clouds, for example, which absorb distant lines of hydrogen from when illuminated by a quasar. So if you look at a quasar at a high redshift, and then all this stuff along the line of sight is creating these absorption lines, and we observe 100 of them and stack them and thereby improve our sensitivity by another factor of 10. Then we have got to the point where the redshift of this object should be actually drifting per year by about 1 part in 10 to the 8, and that's something that this laser comb can measure. So as you see here in this plot here, the expectation of the cosmological model which is decelerating and the one which is accelerating are clearly separated. These are estimated uncertainties for this instrument. These blue points and yellow points should be able to tell the difference. So we will essentially be able to tell by making measurements at 2 points apart in time whether the expansion rate is actually accelerating, because we all know that acceleration is the difference between velocities measured at 2 points in time, and so far nobody has done that. For that we need to do real-time cosmology, and that is coming. So there is a lot in store for those of you who are interested in cosmology in the coming 10 years, and I really think we'll see a major revolution and a overturning of the present paradigm. Uh, and I look forward to the work that our next generations will do in this regard, to go back to ground zero and start reconstructing a model of cosmology based on observations rather than on philosophical principles. So I'll stop there and take any questions. Thank you very much.
So thank you for the lovely talk, sir. Really makes you question how we do science these days around us, and how we should question our fundamentals more than blindly pursuing all the possibilities.
Yeah.
So as I said, we'll be taking any questions, and if anyone has any.
You can also type them into the chat box.
Yes, sir. I'll make sure. So it seems there aren't any questions, sir. Thank you for the lovely talk again. Okay, there seems to be a potential negative. Why was the potential negative and directive Lagrangian?
Can you repeat that, please?
Lagrangian, so why was the potential negative? If we add T minus B, you know that was T plus.
Oh, why is the pressure negative of the energy density?
Yeah, a potential.
Yeah, that's because the lambda is supposed to be this vacuum energy is a fundamental property of the field that occupies space-time. So it should be the same, look the same to all inertial observers. So the metric therefore is not only diagonal, the sum of the diagonal component should be 0. Otherwise, it would not be invariant for all observers. So if you can think about it literally, if I take a volume of space-time and I expand it, if it can say it contains some particles, all that happens if I make the box bigger is that the particles become more dilute, right? Yeah. If there is radiation in my box, then the photons are bouncing off the walls. And as I make the box bigger, because of the bouncing off, they lose energy, so they get redshifted. But if I have just got vacuum energy in this box, if I make a bigger box, then I have more vacuum energy, right? So that is why it actually acts effectively as negative pressure, because a positive pressure would lead to less energy, whereas what I actually have is more energy. So that's one way of thinking about it.
Thank you. Okay, second question, sir. If we give up the assumption of homogeneity and isotropy, then how much the factor 10 to the power 60 in rho lambda modifier?
Sorry, can you if we drop the assumption of isotropy, then what?
Isotropy and homogeneity. So
yes.
Then how much the factor 10 to the power 60 in rho lambda modified?
Oh, but that problem was framed only in the context of the standard model. Uh, I've not said that we have necessarily any solution. Uh, that problem does not go away regardless of what cosmological model you construct, because that is a problem of field theory coupled to classical gravity. Okay, that problem has nothing to do with the cosmological model. What I was talking about is the fact that we ignored that big problem and then we inferred a very tiny value of lambda from observations. Okay. So we really ought not to do that when we don't have the faintest idea about how to solve that factor of 10 to the 60. Right. It may be, as I was suggesting, that there is some very profound, deep reason which we don't know, why nature has decided that vacuum energy does not couple to gravity at all and cannot do so. In which case, I mean, that would be a possible explanation for why we have not already collapsed or gone into exponential expansion dominated by the vacuum energy of quantum fields, which we know are all around us, right? You and I are excitations of quantum fields. Why does our 0 point energy not cause the universe to have a runaway collapse or a runaway expansion? That problem has not gone away and will not go away. That will need a different revolution. As I said, that is arguably the biggest problem in theoretical physics.
Hello, sir. Thank you for the talk. I have a question regarding the Hubble's tension. Even with the 2018 Planck result, the tension still exists. Yeah, but the value is getting smaller. Like the difference is getting smaller, but the tension still exists.
You're talking about the Hubble tension.
Yes. Is it because we are doing something wrong with the observation, or is it something with the fundamental issue?
Well, I'm not sure what people mean by the Hubble tension, because that suggests that you are measuring the same quantity in two different ways, and you are saying that there is a difference between the values that you are measuring, right? Now, the Hubble parameter is a well-defined quantity of the model at the time of the decoupling of the microwave background, so you can infer it from the CMB data. But it is not clear to me that in today's universe, which is extremely inhomogeneous, there is such a thing as the Hubble constant. I mean, the Hubble parameter actually depends on what direction you're looking at. It actually varies by about 10% of the sky. So when people tell you that they have measured the Hubble constant to within 1%, it means that they have made corrections for all these peculiar velocities. But in fact, those corrections have been made assuming a model. It cannot be done in a model independent manner. So therefore, I think the problem is pretty not very well posed. If I can give you an analogy, it's like say my saying that I measured the size radius of the Earth to 1%, right? What you should ask is the Earth a sphere to within 1% precision? In fact, the Earth, as you probably know, is a geoid. It's got excursions from the spherical form, which can go up to 100, 200 kilometers, right? It's got deep trenches. It has got mountains, which are all departures from the spherical shape. So it's not sensible to say I measured the radius of the Earth to 1% when I can't even define the real Earth is not really a sphere to that accuracy.
Thank you.
Any other questions? Okay, I think we are done here, sir. So again, I'd like to take this opportunity to thank you and welcoming us, gracing us with your presence on Friday. Sure, we are busy about for talks and everything. Again, thank you, and I hope you have a good day.
Okay. Thank you very much. If you have any further questions, you are welcome to email me later.
Sure.
Okay. All right. Bye bye then.
Bye, sir.